We live in a world completely overflowing with information. But what happens to the knowledge that seems too strange, too new, or too technical to ever make it into the news? Our entire future is often hidden in plain sight, recorded deep inside dense academic papers with titles like Using Nature's Smallest Architecture to Encode and Safeguard the Human Record and Information Residency. The world is absolutely swamped with digital information. Every 24 hours, people and computers generate more data than our current technology can possibly store. We constantly run into storage limits. Hard drives get full, massive cloud servers pile up everywhere, and we keep running out of space. But a major breakthrough is coming soon. A device about the size of a shoebox that will be powerful enough to store all the information a person could collect in their lifetime, and then some more. SATA hard drives typically fail within 3 to 5 years, while solid-state hard drives last longer, about 5 to 10 years. Even magnetic tape, which is currently our most affordable long-term backup, rarely lasts more than 30 years. Essentially, our best digital storage systems are only temporary, but nature found the perfect way to solve this storage problem thousands of years ago. Here, we are introduced to the concept of DNA punch card. Instead of making the DNA the ink for writing out the data, the DNA is repurposed as the sheet of paper where information is written directly into the DNA's physical structure using nicks or breaks in the sugar phosphate backbone. It's the equivalent to punching tiny, permanent holes in a molecular card. This approach leverages the natural DNA and offers a cheaper and faster path to molecular data storage. The DNA punch card system relies on a kind of molecular surgery where we mar the surface of the DNA strand. Marking this mark on the DNA strand is referred to as nicking. Perfecting this technique for modifying a molecule so small has created a new toolkit for scientists, moving far beyond just data storage. When you can precisely nick and manipulate DNA, you theoretically gain the power to program life itself. We are entering into the weeds at this point. The biggest challenge in building DNA storage was finding a better way to write data. Early methods for making small data-carrying cuts in DNA were slow and limited. The enzymes used back then worked only at certain sites and could make just one cut before failing. The research team solved this by switching to a very different enzyme. This new enzyme is a tool that is much faster, works almost anywhere, and can be reused many times. It also relies on simple, low-cost DNA strands as guides. In testing, it let the team make many accurate cuts on a single DNA strand in less than an hour, turning the idea of a DNA punch card into a practical option for high-speed data storage. At the advent of precision writing on the surface of DNA, turning a digital file, like a photo or document, into a DNA punch card is simpler than it sounds. The file is first converted into a string of ones and zeros. Then a basic rule is applied to a DNA strand, which serves as the card. A 1 means you make a tiny permanent nick in the strand, while a 0 means you leave it untouched. This design is a big advantage. In many other systems, both ones and zeros require some amount of work, but here only the ones do. That cuts the work time and cost of writing data almost in half. It's similar to how data is stored on a CD. Burned pits represent one part of the code, and the flat areas represent the other. And because the DNA strands, sequence, and length are known ahead of time, reading the data is simply a matter of finding the nicks. The result is a fast, efficient, and durable molecular record. To boost data density, scientists added 3 upgrades. They use DNA registers that can coexist independently to write multiple files at once. They allowed nicks on both strands to raise capacity by about 58%, and they use strand grouping and mixing to pack in even more data. The incredible efficiency of using DNA structure like a punch card solved the biggest problem, creating cheap, super fast molecular data storage. But the real bold goal of this research isn't just a better hard drive, it's what they call data residency. To pull this off, scientists want to combine efficiency with precision. They plan to use the nicking method to encode data onto a replica DNA strand, creating a perfect, self-contained record to put into a common living bacterium. They would swap the natural DNA with this synthetic copy. The bacterium would then multiply, creating a genuine living copy of that synthetic record with every reproduction. The final prize isn't a disk or a server, it's the ability to protect all human knowledge inside a living, self-maintaining organism. The storage needs no power, no drives, and no maintenance. The encoded data is entirely independent and incredibly stable. Hidden within a simple cell, it becomes the ultimate molecular time capsule, designed to survive technological collapse, natural disasters, and the simple wearing away of time. It secures the human record using the fundamental language of life itself.